begin learning about bonding. I know I look a little overdressed for the occasion, but this was a dress-up day at the school where I teach. To understand bonding well, you probably need to go back and learn about orbital notation, electron configurations, and electron dot formulas from the previous unit of instruction. Today we're going to be learning about bonding. Bonding. This is bonding between atoms. Okay, write an orbital notation for beryllium and another orbital notation for oxygen. Write an orbital notation for beryllium and another orbital notation for oxygen. So beryllium is a metal, and metals tend to lose electrons. Since beryllium has 2 electrons in its valence level, it's going to give up both those electrons, which now means it will have 2 more protons than electrons, and it will have a 2+ charge. Any ions that have a 2+ charge, or any kind of positive charge, is called a cation. That's a positive charge, and it becomes a cation. Now, conversely, oxygen is gaining 2 electrons, so it's going to have 2 more electrons than protons, and that will give it a 2 negative charge. Electrons have a negative charge, protons have a positive charge. So an ion that has a negative charge has a name called an anion. Negative ions are anions. So nonmetals tend to become anions. Now this is the way ionic bonding works. Positive charges tend to be attracted to negative charges and vice versa. So the beryllium, which has a 2+ charge now, is going to be attracted to the oxygen, which has a 2 negative charge. And that's the idea behind ionic bonding. Negatives are attracted to positives. So the orbital notation for hydrogen, hydrogen has just 1 electron. It's in the s sublevel region. These first 2 columns of the periodic table are the s sublevel region. And so we're going to have just 1 electron in the first orbital. So it just looks like this. Oxygen, we said, is in the second primary energy level, so you already know what its orbital notation looks like. We did it here. I don't know why I did that. They go up here. That should be 2s down there. Okay. Now, when it comes to nonmetals, hydrogen is a nonmetal, oxygen is also a nonmetal. We said that all the elements on this side of this stair step in the last unit, all the elements on this side of the stair step except hydrogen are metals. Hydrogen, when we talk about metals and nonmetals, actually belongs over here. We're talking about S, P, D, and F sublevel regions. Helium actually belongs over here. So you got to kind of know that hydrogen and helium belong in this section or this section, depending on the context. All right. Nonmetals do not give up electrons to other nonmetals. They don't gain electrons from other nonmetals. Nonmetals don't give up electrons or gain electrons from nonmetals. They share electrons. Okay? And so hydrogen will want to share an electron with oxygen, giving the hydrogen 2 electrons. And giving the oxygen, this oxygen anyway, now has 7. But as we know, they want to have how many? What's that rule called? What? Really? It's just the last unit. We just finished this stuff. How many electrons do most atoms want to have in their outer energy level? 8. What do we call that rule? Octet rule. Okay? So in order for oxygen to have all the electrons it would like to have, it needs to share another electron with another hydrogen. And so here's another hydrogen with another electron to share. And so this is sharing going on. And the sharing then gives hydrogen 2 electrons filling up its valence level. And the oxygen gets 8 electrons through this sharing process. giving it all the electrons it wants in its valence level. Okay? And this sharing of electrons happens between nonmetals. It doesn't happen between metals and nonmetals. It happens between nonmetals primarily. Okay? So they're sharing, so we might call this co-sharing. Okay? And it's happening with the outermost energy level electrons. What do we call those? Valent. So that's a covalent, for covalence, the valence level. Covalent bonding, or covalent bond, and then covalent bonding. So nonmetals share electrons with other nonmetals, forming covalent bonds. This is called covalent bonding. Co means two things are together. Valent means these electrons come from the valence level electrons, those electrons in the highest primary energy level. Valence electrons are those electrons in the highest primary energy level. Yeah. All right, so when atoms share electrons, they're also sharing orbitals. When atoms share electrons, they also share orbitals. Sometimes this sharing of bonds, or sharing of orbitals, is called overlapping of orbitals. And I should say sharing of orbitals here, not sharing of bonds. Okay, now if we're going to show this overlapping of orbitals using orbital notation, it's a little bit complex, and later on we're going to be showing how they overlap using balloons and balloon models. But for right now, let's show how we actually get these orbitals together, or try to illustrate that using orbital notation. The problem with this is that this is not showing the actual shape of orbitals. We've talked about this in the last unit, that the orbital notation shows a kind of organization of electrons. It doesn't show the actual shape of the orbitals or what the electrons actually look like or anything like that. It's just organizing the electrons into a kind of bookkeeping system, okay? But if I wanted to try to show somehow that we have overlapping orbitals, I might do it like this. So let's put oxygen kind of at an angle here. And then I'll kind of stick hydrogen in from the side to show how it's sharing those orbitals. I'll just put hydrogen in here like this, and we'll put those electrons like that. Okay? That might be one way we could show how we share orbitals. Okay? And those shared orbitals, the sharing of electrons and the sharing of orbitals, are called covalent bonds. No, I'm just showing you how it goes together is all I'm doing here. So this hydrogen we're saying here, I've moved it down here just to show how the electrons are being put into the same orbital. And I moved this hydrogen down here to show how it's being put into the same orbital. Of course, that's oxygen over here on this side. Again, it's kind of complex to show it that way. Imagine how I might do this if I had larger or more complex atoms. It would really get complex then, wouldn't it? Yeah. And so in order to deal with this problem of showing how bonding occurs, Lewis dot formulas were invented. Okay, Lewis dot formulas were invented. And you remember Lewis dot formulas. We did this in the last unit. I hope you remember it anyway. So write the Lewis dot formulas for hydrogen and oxygen. Write the Lewis dot formulas for hydrogen and oxygen. So a college professor invented Lewis dots, Gilbert Lewis, for the very purpose of showing how electrons are shared between atoms to make it a little less complex. All right, if you did the Lewis dots, then you know that hydrogen has one Lewis dot, and oxygen has how many? What? 6. 1, 2, 3, 4, 5, 6. Okay? Oxygen has 1, 2, 3, 4, 5, 6 electrons in its valence level. 8 electrons is all the electrons. The Lewis dots, or the electron dots, only show those electrons in the highest energy level, the valence level. It's called covalent bonding. We need electrons in the highest primary energy level. And so if I have another hydrogen here, I can show how they're sharing kind of like this. All right? And we're going to call this kind of drawing a sharing arrangement, just to show that's what's going on. All right, so once we get this sharing arrangement, then we're going to put everything together. We're going to take the electrons that we're sharing and sort of squeeze them in between the atom symbols here. So I'm going to take this oxygen and spin it 90 degrees this way and show how I'm sharing and squeezing these electrons in between the hydrogen symbol and the oxygen symbol. So it looks like this. There's those two shared electrons between that hydrogen and that oxygen. And over here, these two are shared like this. Okay? And then the two electrons that are left over, those have to stay there too. Those are called lone pair electrons or unshared pairs. Okay? So just for terminology purposes, to make sure everybody's clear, these electrons here are called shared pairs. No, not Care Bears. Shared pairs. Okay, sometimes called bonded pairs. Okay, that's a shared pair, a bonded pair, that's a shared pair. And then the ones on the top, those are called lone pairs or unshared pairs. So those like that are unshared pairs or lone pairs. So, okay? So we're going from this sharing arrangement to this, and this arrangement here is called a Lewis dot formula. A Lewis dot formula. Okay? We're taking an electron dot formula. This is an electron dot formula. This is an electron dot formula. We're putting it together into a sharing arrangement and then transferring that over, condensing it a bit to get this Lewis dot formula. Okay? Now you guys know this by this formula here. Okay, you've seen that before. And that's the formula for water. Now, if we were to use what's called the IUPAC naming system, IUPAC, I'll give you what that acronym stands for here in a minute. We would name this according to how many atoms we have in the formula. So if we were using the IUPAC system, we would call this dihydrogen oxide. Yes, di for two hydrogens, and then oxide. So the last element in the covalent name, the covalent bonding name, is always changed to IDE. So negative ions, negative monoatomic ions, have an IDE ending as well, and so does the last element in the name in a covalent formula. Okay? So this is going to be called a Lewis dot formula. Or you could also call it a Lewis dot structure. Later on in another unit, we'll learn that these kinds of drawings are called structural formulas. Okay. Well, let's see. Let's go on here. Atoms share electrons in pairs. Atoms share electrons in pairs. Either 2, 4, or 6 electrons. And we're seeing an example here of 2 electrons shared between 2 atoms. 2 electrons shared between 2 atoms. Okay? And when two atoms share two electrons, one from each atom, this is called a single bond. When two atoms share two electrons, one of those electrons from one atom, one of those electrons from another atom, it's called a single bond. So this is the single bond here. Two electrons shared between two atoms. So this is a single bond here. This is another single bond here. Okay, two single bonds in water. When two atoms share four electrons, two electrons from each atom, this is called a double bond. When two atoms share four electrons, two electrons from each atom, this is called a double bond. And when two atoms share six electrons, three from each atom, it's called a triple bond. So a double bond is called a double bond because there are two shared pairs between two atoms. And a triple bond is called a triple bond because there are three shared pairs between two atoms. Okay, let's practice. Figure out the Lewis dot formula for a combination of fluorine and hydrogen. Figure out the Lewis dot formula for a combination of fluorine and hydrogen. I've done water for you, a combination of hydrogen and oxygen. Now you need to figure out how to do a Lewis dot formula using hydrogen and fluorine. Now I'm going to give you a hint just to help you out here. Okay, fluorine needs 8 valence electrons just like oxygen did, and hydrogen is going to need 2 because hydrogen only needs to fill its first valence level. Okay, that would be completely full for hydrogen. It only has 1 valence level, only an S sublevel, and that's all it needs. Yes, the stuff we just did, the Lewis dot formula. So show me the electron dot formulas, then show me the sharing arrangement, then show me the final formula, or the Lewis dot formula, and then see if you can write the formula for the final product, how you put the two elements together, like we put water together, H2O. That's called the molecular formula. H2O is a molecular formula, or just a chemical formula. See if you can do the same thing with this when you're done. All right, so hydrogen has 1 electron dot. Fluorine has 7. 1, 2, well, actually I should say 1 on each of the 4 sides, and then pair them up. So that would be 6 and 7. And then if I share electrons, it'd be like this. Okay? And so if we're going to do a formula for it, so now fluorine has 8 electrons and the hydrogen has the 2 it needs. Let's figure out the Lewis dot formula for a combination of nitrogen and hydrogen. Lewis dot formula for nitrogen and hydrogen. All right, guest teacher. Here we go.
No, I don't. All right, so what you got to do? Wait, what is it again? So then it's got to be. That's what you have to do, right? You gotta do that first. You have to do this first. Alright. What's the other one? Nitrogen? Two. No, it doesn't, bruh. Oh my god. 2, 4, 6, 7. Wait. It only has 7.
Yeah, 7, bro.
That's right.
No, it's not.
It's 7. You have to have 7 for this one. Huh? 2, 4, 6, 7. But aren't we doing nitrogen?
What happened to 5?
2, 4. Oh my god. I swear I'm not that dumb, y'all. Alright, so then you gotta get this. You gotta do the circle thing. Can I just put a circle and then the dot? Is that how it is?
You write a.
Can y'all just be quiet? Dang.
I'm kind of lost too. So what circle you're talking about?
Just do the regular.
All right, man. Whatever. So you gotta 1, 2, 3, 4. No, hold up. So N 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, and you need 3 more, right?
No, that's how many you start. Well, you're gonna need 3 more eventually. Yes.
So then you have to do the thing, right? I don't know.
Which thing are we talking about here?
You have to move you gotta give hydrogen.
Yeah, you got to have hydrogens in there, so that nitrogen has 8 electrons and hydrogen has 2 each.
Somebody want to finish this? Cause I kind of got lost. Cause then I forgot. Come here, Eric. Help me out, man. Don't you give hydrogen like that?
Get it right there.
Hold on. Let's put it on camera. All right.
Alright, then you write the H. And it has 1. Those 2.
That's what I was thinking. Okay, alright, yeah. What is that?
It's an arrow, bro.
For what, though?
To show.
You gotta do the arrows? Which is how you have to make the arrows?
Okay, so nitrogen right now has only 5 electrons, and you left one off somewhere. No, you got 6 electrons, but it needs 8.
Whoa.
Nitrogen needs 8 electrons.
Oh, so you add another. You add hydrogens.
Huh?
You add hydrogens.
Yeah, you got to have more hydrogens to make it work out.
Because it has to be even.
Yeah, okay.
I could do it somewhere else, I
I'm
guess.
gonna bring it right here.
I said 2, 4, 6. That's crazy.
Good. Now the nitrogen has 7 electrons. I need one more electron on there somewhere.
I got you, bro. Dang.
Huh? You got to show the work, but you don't have to do it in separate steps like they did. I'll show you in a second. Okay? As long as you finally get the answer and you show all your work properly, that's all that really matters. Okay? And they're working it out. They're eventually getting to where they need to get to, but you know we can do it all. It's kind of on one step there. Okay?
You have to draw where the nitrogen and the hydrogen, like the loop around the.
Wait,
You have to show that the sharing of the electrons. Yes.
So childish.
Right, so what do we add under H?
Alright,
You got one more hydrogen somewhere, don't you?
Yeah, but where do I put it? Like,
Oh, wait a minute. What'd you do? I can't figure this out.
I just need to.
You need to put that third hydrogen on the bottom.
Yeah, on the bottom.
Yeah, well, I don't know how you got that, but
Is that it?
yeah, you kind of left a hydrogen off somewhere. Let me show you how to do this. All right, you got to get to the point where all the atoms except hydrogen have 8 electrons, and the hydrogen only needs 2 because it only has 1 primary energy level, which has only an S sublevel. So you have hydrogen with 1 dot and nitrogen with 5 dots. And so if I share just 1 electron, this is where they started right here. That gave hydrogen 2 electrons, 2 valence electrons, but nitrogen only has 6 at the moment. So if I put another hydrogen on here with another dot, because for the 1 electron it starts with, and share this one, well, now this hydrogen has 2, which is what it wants, but nitrogen has 7. So now I realize I need 1 more electron somewhere, and so I put another hydrogen down here, and now All right, and so that's the electron dot formula for a combination of nitrogen and hydrogen. Okay? Now, I think a moment ago, did I not tell you that a combination of hydrogen and oxygen would be called dihydrogen oxide? Yeah, okay. So we could call this trihydrogen nitride. Okay? This is your periodic table. I think you left up here, isn't it? Anyway, so the thing you got to know, let's find the periodic table that you have in your packet of electronegativities. The one with electronegativities. Generally speaking, and not always, and this is an exception I want to tell you about in a second, generally speaking, if we use that IUPAC system I mentioned earlier, IUPAC, we're going to write the name of an element symbol for the element with the smallest electronegativity first. Okay, there are exceptions to that. So hydrogen has a lower electronegativity than nitrogen does. So if we're using the IUPAC system, generally speaking, we're going to name this as trihydrogen nitride. Okay? Trihydrogen nitride. If we're going to put it together as a formula, trihydrogen nitride would be written as H3N. Okay? Now, that is not the common name, and this is one of those few compounds for which you have to know the common name. Water's a common name that you need to know. When you see H2O, you need to know that's water. When you see this compound or this compound, you need to know that this should be written as NH3, and it should be called ammonia. Okay, it's just one you have to know. All right? Okay, let's try this one. Let's do a Lewis dot formula for a combination of carbon and chlorine. Now in this case, carbon needs 8 electrons and chlorine also needs 8 electrons. Okay.
I should do like a whole point for this.
Maybe so. We're going to give you another guest teacher here who's going to try this out. All right, explain it to everybody now while you do it, okay?
Oh, okay.
You want to use a dart marker or you use a pencil?
I'm going to use a pencil first in case I didn't know.
All right, be respectful now. Give her your attention. Be respectful and give her your attention.
Okay.
Go ahead. We're waiting.
Okay. I'm going to write it first and then I'll explain it.
Now if she gets off, it's respectful to help her, okay? We just don't, interrupt what she's doing.
Okay, carbon has 4 dots and chlorine has 7. And they both need to have 8. So carbon is going to let chlorine borrow 1. Okay. And that will be just so for chlorine. Now carbon has to have 8 too. So can you see it? Okay, yeah. Okay. And like carbon has to have 8. Okay, yeah. Like step by step, chlorine is gonna let carbon borrow technically 4, but you have to like show your process. So let me get there. Wait. Okay.
You could do all 4 of it at one time if you wanted to. You don't have to do them in separate steps like I did before.
Mm-hmm.
So just put a carbon here and put 4 chlorines around it. That's what you're going to get eventually, but you're just doing it the long way.
Okay. So you want me to do it
Put
like
4 dots around carbon. 4 dots around carbon. All right, there's one at the top. You got a pair at the top. Move the one on the right to the side. There needs to be one on each side, okay? One there and one there. There you go. Now, put 4 chlorines around there.
Like in each side again?
Yeah, it doesn't matter. Yeah, you can put 4 on 4 sides. So put a chlorine here, 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 and down there at the bottom. And then they have, each of those have 7 electrons. So put 7 electrons around each carbon, each chlorine. And then share. There you go. That's it. Well, don't split those up. So you see how this is a pair on this side of this chlorine? Instead of sharing that one, share this one with that little one down at the bottom. You don't want to split up pairs of electrons, okay? That'll work. Okay? Oh no, you erase. You had enough electrons, you erase one somewhere. Let me see your pencil a second. And I'll get you fixed back. All right, this is perfectly okay. Now, can you put it together into a Lewis dot formula? That's like this right here. Put it together now. Now you got that's a sharing arrangement. Now give me the Lewis dot formula.
Do something for this one?
And you got to put all the other electrons around there. So each of those carbons need 1, 2, 3 pairs of electrons around it. 3 pairs, not just 3 electrons, 3 pairs. See how you had 3 pair around it here?
Oh, and
So
I
you need
took
3.
it. Okay.
Yeah, you got to keep them. No, not between them. Put it on the side over here. Take those out at the bottom and put it over on the side. There you go. That's the idea. That's it. All right?
Lock. Now, do I look for something for chlorine? Or is
That's
that
it.
answer?
That's the Lewis dot formula. You're done.
Oh, I'm done.
You're done.
Is that a whole point for credit?
No, I have to give you what I give every time. All right, let's do this practice problem. Combination of sulfur and fluorine. Sulfur and fluorine. Sulfur and fluorine. All right, one more time. Guest teacher here. All right.
I don't like this.
Fluorine's only going to have. All right, go ahead and put another fluorine up there. Don't do separate steps. Up in your first drawing, put another fluorine up there.
Okay. I was just showing which one has.
Oh, I got you. Okay.
How they
Now,
all
go ahead
have.
and show the sharing right there. They don't have to be pretty. Just loop the circle around an electron from fluorine
Can I
and
use
an
your
electron from
highlighters?
sulfur. Well, if you want to, if you think it'll work, sure.
How did I do that?
Well, I don't know what you're doing.
See,
I'm
I was
suggesting-
just circling it to show how they.
But what I want you to do is to show how they
See.
actually share. So you can share this one here. Okay?
Okay.
Now show how that other one shares.
Okay.
You got one more pair of electrons to share.
Like, when you share electrons, does it have to
It
look
looks so messy.
can it look different?
There's nothing wrong with that, though. Put it on camera so we can see it.
Sorry.
There you go. There's nothing wrong with that.
Yeah, I know. I'm just saying, does it have to look like that? Look at mine.
I know. I was drawing like little circles
Yeah, like that. The same
instead of like.
No, you share 2 electrons with fluorine. Fluorine has 7 electrons, and then fluorine has 9. You only need 8 with fluorine.
Oh, it's different. Oh, snap. Right. You want us to push them to so it's
Yeah.
two fluorine.
Yeah, but you need to have. Yeah, you have. I would do it right. You have 2 fluorines. That's what she has right there.
I'm sorry.
I don't know.
I thought you said it would be 240.
Y'all need to listen, especially Adrian.
What are you talking about? I am a savage. I did do this right. What's up with you?
Right?
You got 2 more electrons to put on the fluorine.
Alright.
Yeah, I was getting there.
That's it.
Oh,
Getting there.
I didn't put the top on this time.
Okay. All right.
you can just
Okay, listen up. Now you don't have to have the fluorines on the right side and the bottom. You can put on any one of the 4 sides. Okay? How it gets arranged doesn't matter as long as the electrons are lined up properly. Okay?
Can we do one more?
Well, I kind of need to move on today to some other things here. Okay? We're going to continue to talk about electron dots, but I don't want to stay too long on just the single bonds. Okay? So sharing 2 electrons is forming a single bond. All right? Sharing 2 electrons is forming a single bond. I want to talk about this way of naming things we've been talking about here, okay, before I move too far ahead. We said that the first one we did could be called water, but its formal name, its IUPAC name, would be dihydrogen oxide. And the next one we did was to be called trihydrogen nitride in the formal system. And now we've got a system here where we've got a sulfur and 2 fluorines. And let's see, find the periodic table has electronegativities, and sulfur has a lower electronegativity than fluorine does, so we'd name sulfur first and write the symbol first. So it would be SF2 for the molecular formula, and the name would be sulfur difluoride. Okay? That's how we write the name. We write the sulfur symbol first and the name, and we write sulfur in the name first, because in general, not always, in general, you write the one first that has the lower electronegativity. Okay? The one that's closer to the lower left-hand corner of the periodic table, because those have the lowest electronegativities. So let's talk about this naming system here a little bit before we go too far. When we're using these prefixes, we said that water was dihydrogen oxide, di for 2 hydrogens, and nitrogen was trihydrogen nitride in the formal name, the IUPAC name. All right, so we're going to be using prefixes for naming like this, okay? So di is for 2, tri is for 3, tetra is for 4, penta is a prefix. What happened to my screen? And tri is the prefix for 3. And tetra, the prefix for 4. Penta is the prefix for 5. Hexa is the prefix for 6. Hepta is the prefix for 7. Octa is the prefix for 8. Nona, prefix for 9. Deca is the prefix for 10. Now, you notice I didn't list a prefix for 1. The prefix for 1 is very rarely used. The prefix for 1 is very rarely used. The kind of exception to using the prefix for 1 is this formula here. Okay, that is carbon monoxide. Okay, carbon monoxide. Now, carbon monoxide is not as common as carbon dioxide, and it's also poisonous. Carbon dioxide, I mean, if you have too much of it, it still can kill you, but it's not considered poisonous. So we're naming covalent compounds. We're using this prefix system, and we're changing the end of the name of the last element to IDE. Okay? So that's why we have this sulfur difluoride. Okay? Now this only applies to those covalent compounds, nonmetals, covalent compounds that are non-organic. Okay? Organic compounds have a completely different naming system. Now what is an organic compound? Organic compounds, with some exception, are those covalent compounds, all nonmetals, covalent compounds that have two or more carbon atoms bonded together. Two or more carbon atoms bonded together. There are a couple of major exceptions. All right. If I were to bond just two carbon atoms together, that would make an organic compound. Of course, I need other things on there too. Yes.
Can you take a time, like before people go to RD to explain the project we have to do?
All right. So this would be an organic compound, but there are two organic compounds that you got to know about that are not those that have carbon atoms bonded together. Okay? Two exceptions to this about the carbons being bonded together. One of them is methane. Methane just has one carbon and four hydrogens. And the other is carbon dioxide, which is CO2. Okay. Now we said earlier that you can have more than two electrons share between two atoms. You can have more than two electrons share between two atoms. Let's look at carbon dioxide here. Carbon dioxide. Carbon dioxide has one carbon and two oxygens. Okay? So how many dots or electron dots do we put around carbon? How many electron dots do we put around carbon? 4. 1, 2, 3, 4. How many electron dots do we put around oxygen? 6. 1, 2, 3, 4, 5, 6. But I need two oxygens. 1, 2, 3, 4, 5, 6. Now that's all the atoms we have, and we've got to arrange things so that the carbon and both the oxygens have 8 electrons. If I share one electron here, this oxygen has 7, this carbon has 6. If I share one electron here, this carbon now has 6, and this oxygen has 7. So what I can do then is to share another set of electrons, and now the oxygens all have 8 electrons, and the carbon has 8 electrons. And the way that we write that out in a Lewis dot formula is to put the carbon here in the middle, and since I'm sharing not 2 pairs, but 4 pairs, I'm sorry, not 1 pair, but 2 pairs, I'm sorry. Not 2 electrons, but 4 electrons. Okay? They're going to be put between the carbon and the oxygen in this fashion. And over here on this side, they put between the carbon and the oxygen in the same fashion. And the remaining electron pairs get left over here on the sides where they belong. Lone pairs, here and here, and now we've got a double bond. 2 shared pairs making a double bond. 2 shared pairs making a double bond. let's do a combination of 2 carbon atoms with 4 hydrogen atoms. Okay? Let's do those right now. 2 carbon atoms and 4 hydrogen atoms. Okay? So this is the solution. This is the solution. We have to double bond the carbons to make this work out. And we get this double bond here.
I did that, but I didn't know that we could leave
Okay.
one side of the letter blank, like with no dot.
And then your homework is to do these 3 problems here.
Okay.
Okay, so carbon dioxide, the only way to get the carbon to have 8 electrons, 1, 2, 3, 4, 8 electrons around the carbon, and the oxygen to have 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8, is to double bond both bonds to the oxygen from the carbon. Okay, and you get CO2. So here's oxygen, which we just did, and here's another oxygen. And so the only way to get oxygen to have 8 electrons, both of them have 8 electrons, is to bond twice. And we'll get and this is atmospheric oxygen. Okay? So see what you can do with bonding 2 nitrogens together, because it turns out nitrogen forms N2 as well. 2 nitrogens. See if you can bond those together. So the question was, I have a lone pair up here and a lone pair down here. Do they have to be like that? No, I could have put the lone pair up here on this. Doesn't really matter. Unless, when you get further into the way that bonding occurs and stuff, you'll know why we write it like that. There's no triple bond. Oh, for nitrogen?
Yeah.
Ooh. Ooh. Somebody's on top of things.
He's asking questions. You decided you're going to have a complex thing.
Say what?
It'd be 3 in the middle.
Yeah, you put 3 in the middle. All right, so we want the electrons to be between the 2 nitrogens to show they're bonding 3 times. Okay, 3 pairs. So that's a triple bond. That's a triple bond. Okay, that's N2. Okay, very good. All right. No, carbon doesn't bond to carbon that way. You can't get 4 in the middle. It strains the bonding angles. There actually are ways sometimes to get 4 bonds, but it's not something that happens naturally that I know of. Okay. You don't. We only do three bonds. That's as far as we go. Okay. That's all that happens naturally. All right. Okay. Let's see here. Put together 1 hydrogen, one oxygen, and one nitrogen atom. All going to be 1. See if you can do that.
Alright, I'm about to do it. Can you go back?
Whoop. Hold on.
Should have got it.
That's probably right. They should have got it, but you know.
I'm not a slacker. I was. Oh my god.
One hydrogen, one oxygen, and one nitrogen atom. Okay?
Bro, they needed to cancel the game.
Ooh, not flashing time. Nobody took a picture.
I was.
Thank you.
Oh, Connor.
Yes.
He's watching the solar eclipse.
There's not going to be a solar eclipse this weekend.
Bloodthirsty eclipse.
It just so happens that when we're recording this video, there's going to be a lunar eclipse this weekend. A blood moon.
No.
He's really being bothered.
So here's the point, guys. You don't have to line them up nice and neat. Just find out how they pair up. Okay? Nobody's asking you to make it look nice and neat like mine are, because you know what? I already know how they're going to turn out. I've been doing this for a long time, okay? If they look kind of like a bunch of worms on there, that's fine. You got it?
Yes, sir. Thank you for a wonderful lesson. I was so eager to learn today. I learned a lot.
I felt very.
Are you saying that just because I'm recording this?